Okay, Emily, we're ready to roll. Good morning, everyone. My name is Lonnie McGinnis. I'm President and CEO of the Manitoba Home Builders Association. And on behalf of our event sponsors, the Accurate Technology Group and Federated Insurance, welcome to the fourth session of the MHBA's Virtual Housing Forum. Thank you all for attending today's webinar. And now to kick off today's session is a quick introduction of today's speaker, Emily Caron, by our event sponsor.
Hi, my name is Wayne Budge from Federated Insurance, and we're proud to sponsor today's webinar. It's my pleasure to introduce Amélie Caron of the Professional Home Builders Institute. Amélie is a building scientist. She's principal at EcoSynergy, founded in 2009. Amélie has been in the residential building industry since 2001. Her unique multidisciplinary expertise can assist design teams in meeting their energy performance targets by providing timely, context-appropriate, and cost-effective solutions. Amélie has extensive experience in building energy consulting and simulation. She provides technical direction and has participated in several net zero energy home energy modeling and consultations across the country. She is certified LEED for Homes Green Rater and EnerGuide Energy Advisor. She obtained a master's degree in building science and sustainable designs at the Danube University in Austria. Her master thesis was a comparison of the net zero energy home and the passive house in regards to life cycle cost, carbon emissions, construction feasibility, and primary energy requirements. Amélie and her team can assist from design to occupancy of residential projects, offering code compliance modeling, optimization to higher performance, comfort calculations, on-site testing, and troubleshooting and application of aero barrier whole building air tightness technology. All that, and I also happen to know that Amélie enjoys the occasional single malt scotch. Cheers.
Thank you. Hi, everyone. I can't see anybody, so it's a little awkward for me, but I'll do my best to make this work for everyone. So obviously, this is going to be a little bit more of a monologue presentation compared to when we usually do them on stage. But please feel free to mark your questions, and we can answer all of them at the end of the webinar. So I'll just connect and share my screen here, if you're willing to just give me a second. Oh, wrong screen. Give me a second. Oh, I see. I will share the other screen. This one. There we go. Voila. Everybody sees the screen? Oh, I can't hear anybody. You're all muted. Okay.
We can see it.
Okay, thank you. It's always good to get feedback. Okay, so there's a big topic these days about air tightness and energy modeling and how we can possibly make that part of our construction practices. And I felt that Manitoba is a great market to talk about that, because you are all already experts at air tightness. So let's dive in and see how we can make this work and benefit from all this effort that we put forward. So in today's context, NECB 2010 was adopted in Alberta in 2016. And the new code change, the update, is coming around winter of 2021. I understand that it's the intention of the province of Manitoba to adopt the 2021 building code as it comes out from the national level without changes. So when we think about that, what can we anticipate might come out of there? Some might have been part of some work groups. There's a lot of conversations around air tightness, mandatory air leakage targeting. Should we assume that the prescriptive values will be increased with the 2021 code? Or maybe they're going to start asking for a percentage of betterness for the performance modeling, because as of now, it's an equal or better kind of thing. So are they going to start targeting 5, 10, 15% moving forward? Or are they going to lean towards renewable energy and say, hey, you know, just slap on a few solar cells on every house to help offset the carbon footprint of electricity in the prairies? Or are they going to mandate the HVAC teams to actually start designing their HVAC distribution systems to a room by room comfort calculation rather than a floor by floor? So these are just questions that we're throwing out there and say, okay, well, where are we going with all this? So where are the codes going, and what can we possibly anticipate or expect? Are we going to go towards a performance path or prescriptive path? So we're just going to dive into a little bit of a code review so that we're all on the same page. So as you all know, the National Energy Code for Buildings, the NECB, is the overall building code across the country. That code applies to any kind of building. A Part 3 building, a Part 9 building that's more than 600 meters square or 3 stories, so some wood structures. Part 9 buildings that are of residential occupancy. So for the ones that didn't know, there are some buildings that are not residential in the Part 9 of the building code. And in the NECB, the prescriptive path also has a window to wall ratio that's mandated. So what that means is once they've done all the energy review, there's a maximum amount of window and door that's allowed on a prescriptive NECB. So the reason why I bring NECB up is that NECB is the all in all. The Part 936 that we are talking about in the small buildings is the exception or the leniency to the National Energy Code. Just like the National Building Code in its bigger part is made for large buildings, Part 9 of the Building Code is the leniency for small buildings. So it's the same parallel. So in the 936 part of the Energy Code, you have prescriptive, trade-off, and a performance path. So in the prescriptive path, we can do residential occupancy buildings that are less than 20% of common area, and they have to be 100% dwellings, and non-residential occupancy less than 300 meters square. And for the performance path, then we can model only houses. And the reason why we state the appendix is that house is very defined in the building code, and buildings that are less than 20% common area and 100% dwelling. So the caveat here is that the National Energy Code is not 100% in line with the National Building Code, meaning that you can have some commercial use buildings that are small enough to be compliant to the Energy Code in the Part 9 section. And you can have Part 9 occupancies that might be compliant in the NECB. So there is a little bit of overlap. So it's not a direct parallel. So we have to be careful. Now, the different paths. So we all kind of heard them over the times, over the years. So we have a prescriptive, a trade-off, and a performance. So in a nutshell, prescriptive is kind of you have to prove that you get there. The trade-off path really is like a prescriptive, but then you can trade off, let's say, ceiling insulation for walls and slab insulation. And in the end, if the total energy usage is better in what you're wanting to build, then you're compliant on the trade-off path. I feel the trade-off path is a good option in the renovation market. For example, let's say you're adding an extension and there's a flat roof on the top of your extension. Depending on where your windows, or you want to put like the kind of ceiling height you might have at the second floor, there might not be enough space to have a really thick truss system to insulate it to the required effective RSI values. That being said, the code would more than likely allow to have better windows or better wall insulation to offset the extra losses from that smaller space. So we've used the trade-off mainly in renovations. For new construction, the benefit isn't as great. And most of the work that we do anyways is a performance base. So the performance modeling is where everything kind of stems from. And basically there is no minimum spec. The only thing we're worried about in a performance modeling is the total annual energy consumption of what you're wanting to build. So what we do is we compare the same house, so same geometry, but one to the specs you want to build it, and the other one to the minimum prescriptive specifications. The reason why performance allows for a lot of relaxations is that it includes different things than the prescriptive path does. So it includes passive solar gains, reducing heating requirements, it includes air tightness, it includes HRV heat recovery, it includes a whole bunch of stuff that cannot be accounted for in a prescriptive path. So, and the glorious thing about the performance is that there is no minimum. I think market will determine what that minimum is. What I mean by that is if your proposed house, you know, you could get away in meeting code with building, you know, really old insulation values, an R28 attic, R12 walls, and R8 basement. Yeah, in theory, you might just be able to meet code. I'm not saying it's going to sell though, simply because that's not what mainstream builders would do, but it just shows that, you know, there's a lot of value engineering that can go into a performance model. So generally speaking, these are the two paths that are most used in code compliance. So the prescriptive is an all or nothing. You can't do just the attic and the basement, you have to do everything. So all your windows have to comply, your walls have to comply, and then all your HVAC efficiencies have to comply. So it's an all or nothing. The current code in Manitoba has relaxed effective RSI values because of the amendments that were made, but we kind of have to assume that those values will change and more than likely go up as Manitoba adopts the 2021 National Building Code, National Energy Code. Manitoba also requires gray water heat recovery for all prescriptive paths. And as I said earlier, there's no accounting of air tightness or building as a system approach in the prescriptive path. Now, the performance path, it allows for a lot of flexibility in the design. There is no minimum requirements for HVAC and envelope, again, what market will pay for. Gray water heat recovery is not required in the performance modeling. And we can include energy savings from air tightness and HRVs. So I feel that there's not one size fit all. You want to be able to play around with both, but really in our experience, what we've seen is the prescriptive path really benefits high performance houses. So like when you're going to like a passive house or net zero or highly insulated houses, then the prescriptive path is kind of a no-brainer to comply with code. It's easy, it's quick. But if cost is a concern, or, you know, most people want to build houses cost optimized, right? So performance tends to allow us to go in that direction. Now, making energy conservation part of our building codes is always a good way to push an industry forward. I mean, let's face it, we've been building houses for what, almost like over a century now. And as far as I'm concerned, we didn't change much. Like, we're still building with wood, we're still building with bat, you know, maybe the attic insulation changed, but we haven't changed really dramatically the way we do things for over a century. And now we're stuck with a challenge that is very, very time aggressive for an industry like ours. So when we push an industry forward, we have to do it wisely. And we have to integrate the different parts of the codes and not just add them to one another. The reason for that, I'll explain that in a minute. So if we don't carefully integrate all the different requirements of the energy codes, we may create more problems than good out of all this. We have to start getting the building code is currently set in silos. So you have the ventilation piece, you have the thermal piece, you have, you know, the structural piece, and all these different parts of the building code don't refer to one another. They're all in silos. And so if we keep on that track and we don't understand how all these sections interact with one another, we may not be able to build houses in our current developments. We might have structural problems. We might have indoor air quality issues and mold growth in our brand new houses and major envelope failures. So just to give you an example of one of those things that we saw here in Alberta, and what happened here is we were not allowed to have open soffits on the roofs on the side yards, not on all houses. I think if you're 6 feet apart or in those waters, I don't know by heart, you can't have vented soffits. So that, like, when you just state it like that, it doesn't seem like a big deal, but when you really start thinking about it, all of a sudden, to have proper attic venting, now you have to go to a gable roof, or you can only vent from front to back. So now the design of the houses has been impacted by that decision. It's harder to dry an attic space doing that. And so instead of pushing, because the building codes don't dictate bylaws, because again, they're in silos, they're not integrated, then the cities or the different authorities didn't think, oh, we should just spread the houses apart, because the reason why we want to plug soffits is because fire transfers from one house to another when one burns down. So they're thinking, oh, well, we'll keep them really close together, but we're not going to allow open soffits to reduce risk of fire transmission. So basically, we're looking at a rule that says, okay, well, we'll do everything we can so you don't burn down, but then you're probably going to have mold and problem is in your attic, and even attic rain, which is a big topic out here, probably just like your region, and ceilings falling on your head. So, I mean, I understand the intention, but I feel that there might have been a little bit more research when this decision was made. So there's a ton of examples like that where building codes, city bylaws are not integrated in a way that now the builders are stuck in a situation where they have very little control, and they are the ones put to the microscope as far as meeting, the 2030 net zero energy ready targets. So this is what we might end up doing if we don't take this carefully. So adding insulation and only doing that is not a safe way to approach the transition to 2030. If we want to build to 2030 net zero energy ready, we want to make sure that people are going to want to be living in that they will be able to live in them. And the reason why I separate the two is that, when you look at pictures like these with mold and drywall falling off the walls, I mean, some people that have very, very low income, that might be the only thing they can afford, but ultimately their health is going to kick them out of there. So where do we find that balance? So how do we make the transition to the Pan-Canadian framework targets of net zero energy ready by 2030 a success? There's a lot of moving parts, and just like any new trade or new expert that come in construction, that's where performance modeling at the design stage comes in. Currently, the performance path is mainly used as a verification tool to make sure that the houses comply with the different building codes. When we take this approach to the commercial level, the last code change from 2015 to 2017, I think many larger buildings that were compliant by about 5% in the old version are not compliant anymore. And so now they have to treat the performance modeling as a design tool, and that leads every decision they make. You can't go in, but you have to know that when you go to tender, your building will be compliant. Now that hasn't happened yet in residential, but we have to assume that it's coming. So modeling performance modeling at the design stage will become a key component to making this work. The other thing too is because we can't calculate a load, so an energy load, heating, cooling, appliances, electrical load on a trade-off path or prescriptive path, we have to assume that in the future, those paths will disappear simply because of the target from the Pan-Canadian framework. So how do we get to transition without all the risks? The risks of envelope failure, the risk to occupant comfort and callbacks, and how do we do it more cost effectively? So here's a nugget I always like to point out. Many homeowners call back builders after occupancy because of whatever reason. What I think we're missing here is that most of these callbacks are triggered by some kind of discomfort. Now, homeowners don't know that it's a discomfort issue. All they see is the symptom. Symptom could be, there's cold air coming out of my ductwork. I have ice on my windows. You know, whatever the discomfort is, whether it's visual or thermal or breeze, whatever that is. And so they don't know that it's a discomfort trigger, but you get the phone call and now you're trying to troubleshoot something that is very, not everybody feels comfort the same way. So I feel that there's a conversation around comfort. We see it as something that is kind of secondary. But when you really think back at all the calls that you might get after occupancy, you might realize that if we designed for slightly better comfort for the occupants, there's going to be a lot less callbacks. So there's food for thought. And cost is always a conversation piece. I mean, let's face it, we all want to build a good product. We all want to get to net zero energy ready by 2030, but nobody's in business to go under. We need to make this work for all. We need to make it cost effectively. So this is where air tightness and energy modeling becomes your best friend. Now we want to include those two pieces together, and for all the reasons that are listed above. So in Manitoba, it's easy because I have been made aware that the builders in Manitoba are already expert at air tightness due to the push of the Air 2000 program in your region about 10 years ago. So kudos, because that's not what we see in Alberta and in BC, okay? Now, just to be fair, the different climates allow for different leniencies, different relaxations. So, you know, but there's something to be proud of as far as the Manitoban builders in how you can detail the air tightness of your houses. So if you're putting all this hard work, why not use it to your advantage? So let's do a quick airtightness recap. So as this is more of a monologue, usually this is done and we're kind of interacting all together. I welcome you to just kind of think about the questions I'll be asking, and then we can have a conversation around them at the end of the session. So really, what's the intention of an air barrier? What is your primary air barrier? There's a few mainstream ones, but you know, it's all up in the air. Is what you can get really creative. What materials can we use and how do we use them? What are the challenges around air tightness? What are the benefits? Because it's not all just about energy efficiency. There's a lot of other benefits to air tightness. How do we detail it? Now we're getting into what I like to call site babysitting. There's a lot of detailing that goes into a proper air barrier system. What are the cautions? What do we have to be mindful of when we are getting really, really airtight? What does that mean? Can we guarantee an air leakage target, and how do we do that? And when we get into the modeling piece, I'll touch base on that a little later. And how can air tightness ease the performance or the achievements, the achievements, sorry, I'm French, sometimes I kind of just say my words backwards. How does air tightness allow us to achieve either a code compliance, an ERS, or net zero energy cost effectively? So how does that play in this whole solution? So what's the intention of the air barrier system? Well, you probably all know this, but basically it's to reduce the amount of haunted or uncontrolled leaks through the envelope system of your house. And those leaks are mainly triggered by pressure differentials between inside and outside the house. So in the prairies, I guess the only time that we wouldn't get, and that's really theoretical, the only time that we would not get any air transfer from inside the house to the outside is if there's zero wind outside and zero wind inside. So, I mean, if we think about that, it really never happens. So might as well get on the bandwagon and understand how all this works. So basically, there's three main ways that your house loses air, and there's stack effect, mechanical flue effect, and the window effect. So depending on where your windows are located and when you open them, then you can get either cross ventilation, or you can get, if they're closed, pressure planes, so positive negative pressure planes. So this is all part of building science 101. I believe there's a lot of courses out there that you can use if PHBI doesn't already have one. I know they have a huge amount of courses that you can tap into. Okay, so where does the air barrier system have to be located? Now we're talking air here. We're not talking about vapor retarder or vapor barriers. We're talking about air barriers. So again, air barriers can be located anywhere in your envelope system. It can go in and out. It can go only inside, go only outside, as long as it's one continuous tied-in system. I always like to say that you can't have a half-pop bubble. Either it's whole or it's popped. So if you have either an exterior air barrier, you have to tie it to the inside one on the ceiling level, and then tie that to your windows, down the wall, rim joist, foundation, back down to the slab edge, and then all the penetrations throughout that envelope system. So the only criteria that we have to be aware of for an air barrier is that it has to be impermeable to airflow. I'll give you an idea what that means in a minute. It has to be continuous, meaning it has to be sealed, caulked, and taped so that it doesn't move and it resists air. You can't have a hole in it. It doesn't have to be vapor tight. It can be airtight, but it doesn't have to be vapor tight. And that's where some people kind of, they get confused. And the other thing is it has to be durable during the construction process, because, it's great if you put all that detailing in, and then once you're done and all your trades leave, then your air barrier is destroyed because, it's a construction site. So we have to be mindful of those things just to make sure that you're not kind of just wasting your time and money. So what materials can we use? In my nerd world, it's any material that has 0.02 metric perms at 75 pascals of pressure differential. So that's a mouthful. In layman's, for every other people, it's pretty much any material that's not fiberish, right? So, I mean, generally speaking, or grossly speaking, you could just kind of think about this material and hold it up to your face and blow air to it. And if air doesn't go through it, it might be an air barrier. You could use it in an air barrier. So there's a lot of products out there that we can use as an air barrier system. And on the slide, for the ones that can see it, there's a whole list of them. OSB, drywall, poly, polystyrene, anything that's hard really can be part of an airtight system. That would be the primary air barrier. So what is your primary air barrier system? So that is the one or two materials that will cover the greater area of all your components. So in Alberta, a lot of time it's the polyethylene on the inside of the house. So that polyethylene covers the attic, it covers the walls. There's another approach for the rim joist most times. And then, the poly can go on the front part, on the hot side of the frost wall in the basement, and then ties into the slab and even under the slab, right? So the polyethylene in that scenario is the primary air barrier. Now, to make it airtight, you have to seal it all up, right? So you want to seal it up with whatever you can. So what are the challenges of building an air barrier system? Well, it's not something that's taught in school. I mean, I have an architectural tech background, and yeah, okay, maybe I date from 2001, maybe the curriculum's changed. I mean, I knew where to put detailing for vapor barriers, but I don't recall really getting a full course on air leakage and how that works. There's a lot of management on site. Air barrier systems are a real team effort, right from the concrete foundation guys to the structure, to the framers and the insulators and drywallers, and then even the finishings. It can be pretty labor intensive, and it can take a lot of time. Not many understand it. They kind of just do what they've been doing for years, and they don't really question if there's a reason for doing things a certain way. And who's responsible for them? I mean, we have one of our customers here that he's the drywall and insulator guy, and in his contract, he has the air tightness or air barrier liability. I mean, that's a huge liability. So that builder actually just rules out all the other trades and puts the entire onus of air tightness on this one trade. So again, to me, that just shows that there's a misunderstanding of how it is a team effort. So there's a lot of little holes in our houses that need to be addressed, and they're not always as easy to detail as we would like them to be. So what are the benefits of building a performing air barrier? And we'll get into what that means. So what's a performing air barrier? So for the homeowner and client, we can see operations cost reduction in the lifetime of the building. Now, to be fair, right now in history, the cost analysis for energy savings is kind of doomed. It's not very good because their cost of energy is so low. We can only assume that they're going to go up though. So as soon as you get a homeowner that is willing to be in their plans on getting in their houses for 5 years, there's a chance that the energy pricing is going to go up, so that the cost benefit to air tightness is going to be a little better. It allows for better control of indoor air quality and can also promote better indoor air quality. And that's where some groups also get confused, like, well, if I'm too airtight, am I not reducing the indoor air quality? Well, again, we'll get into that in a minute. The houses are usually quieter. We don't hear as much what's going on in our neighbors. I find it really interesting. As I did my master's in Europe, there's this stigma that says, oh, I don't want to live in a row house, or I don't want to live in an apartment because I don't want to hear my neighbors. Well, I don't know for you, but I live in a house, and man, I hear my neighbors. I hear them when they shovel. I hear them when they talk outside my front deck, and I'm detached. So I don't know if it's just this idea or if it's true, but an airtight house will reduce the sound transmission from the outside. In certain areas of the country, it can also be a good pest control. Apparently less ants get in and things like that, just because if it's done really, really well, there's just less room for small creatures to get in your house. And it reduces drafting, so stack effect is kind of cut out. So you won't get the big temperature differential between your upper floor, main floor, and basement as much as if you weren't as airtight. And another benefit that happened recently is when we have attached units or apartment units or condo units. If you compartmentalize them, now you don't smell your neighbors. It wasn't a challenge. People didn't care as much until recently, when the laws around cannabis changed. Because so now it's not just the different foods that your neighbors might make, or if they're smokers, is now people are worried that they're gonna get some cannabis smells in their houses and in their units, and then they get worried about their babies, and so now indoor air quality is becoming a big question. So now the benefits to the builder, it makes energy performance way easier. If you're airtight, and I'll showcase a case study that we've done already just to give you an example, you will find that high performance is very easy to achieve, and you don't have to go wild on assemblies and like, yes, you need more insulation, but I would debate the thick 16 inches wall kind of thing. It mitigates moisture issues in the envelope system. From what I've heard from the warranty programs here in Alberta is that air leakage is the second biggest trigger to envelope failure. So if you're airtight, you have a lot less risks of either attic rain, of condensation in your walls and things like that. Now there's other components to those things. Air tightness is not the only piece, but it certainly is part of the challenge. Cost trade-off on air tightness. So insulation is great, but when you actually crunch the numbers and do the math, you realize really quickly that insulation has a fair diminishing return attached to it. And so to build a house that will perform very well, if you're airtight, now you can relax the insulation values for the same performance and same level of comfort. We're not jeopardizing anything here. It's just air tightness just makes the building all better for the occupants. And again, I'm going to bring the breathing part in a minute. And like I said earlier, you're probably going to reduce some callbacks from your homeowners because now they're not going to be drafty. You're going to find that your distribution system is going to be probably working a little better for your heating, simply because now you're not going to be losing heat or gaining too much heat in different sides of the house because of air leakage and things like that. So there's a lot of benefits around air tightness. There's also a lot of detailing around air tightness. I just really like this slide because when you look at it, you're like, oh my God, that's a ton of work, right? So basically, if you go on site, the air will travel every time you have two hard surfaces together that are linking to the outside. So all those little arrows on this slide, bottom plate, top plate, window perimeter, between window unit and rough opening, rim joist, slab edge, penetrations to slab, sump pump pits, and I mean, there's so much detailing that it's a little overwhelming. So how can we get all this done? Like there's ways, because we've tested houses that were 0.38 changes per hour with conventional practices, and we've tested houses that were, you know, 4. My worst one was 38, but there's context to that. So if you want to know more about that story, just reach to PHBI, I'll explain. But yeah, 38 ACH, that was kind of is a real interesting one. So all this air tightness talk, we have to be cautious about a couple things when we talk about air tightness. So yes, when you have an airtight building, your unit will tend to keep a lot more of its moisture because now the moisture doesn't have anywhere to go. For the longest time, it could just travel through the walls and all the holes in your envelope system, and you'd be just fine, right? So it could also create a challenge in indoor air quality, simply because some moisture is good, but just like anything, too much is like not enough. So you don't want to have it too high. And if you can't keep the relative humidity in check, then that's when you get condensation on windows and potential mold growth on either a thermal bridge on your walls or at the floor perimeter. We've seen that in the past. So the typical response is, well, you know, if I'm so airtight, how is my house going to breathe? Well, I'd like us to change the lingo a little bit. The house doesn't have to breathe, quote unquote, it has to dry. So the way I see a house is it really is a lot like a human body. Now, you know, I agree, if we all wrap ourselves up in saran wrap, we're not going to be happy, right? We're all going to be a little suffocating. Now, if I poke a hole and I put a straw in your nose and mouth, you'll feel a little better, but it's not optimal, right? So, but in a nutshell, human bodies dry and sweat through the skin and the muscles. So our shell is our structure, it's our insulator, it's our air tightness, and our drying or breathing is through an internal system, which is our lungs. So a house can be viewed very closely to that same model. And fair enough, human beings even, you know, cool by their feet and by their feet and heads, and it's the same with a house. And so, I mean, if you start thinking about the parallels, it might help you understand the building as a system. It's not too far off. I mean, we are building houses to our image. So I feel that there is a parallel there to keep in mind. So luckily, every single house has a ventilation system to dry it. And they're called windows. Now you're going to say, oh, come on, Em, you know, windows, really? I'm like, well, it's not energy efficient. It's really uncomfortable. You can't control the amount of air that you're going to let through your house. But ultimately, you know, if you're ready to suck up the consequences, you can open up your windows in winter conditions, and you're going to dry your house. Now, it's not optimal. So what would we recommend? Obviously, you all know it. An HRV is the best way to approach this. Now, again, Manitoba makes heat recovery ventilators mandatory in every construction. Well, that's really good. And I don't know if you ever ask yourself, so why? But basically, because the Manitoban builders are already very well versed on air tightness and they reach really good targets, you have to have proper ventilation. And that is also why they were able to, the different governments were able to relax the prescriptive values in Manitoba, because they know that the builders do a good job of air tightness. So again, kudos to you. Now, those HRV units, yes, we need them and we should be putting them in, but is there a way that we could, so an HRV could be anywhere from what, $700 to $1,500? I don't know. Depends on your market, depends on your unit. But is there a way that we could fit the price of that unit in your current budget rather than adding it to your budget? Now, I understand that you probably plan for the expense on your build, but can we make up that money in our pocket? And then you get to choose what you want to do with that extra money, right? I'll leave that up to your business savvy people on your teams. So, ventilation systems and heat recoveries. As HRV recovers the heat from the exhaust air rather than discard it, it saves energy as it preheats incoming fresh air. Now that's a true statement, it does. But again, because of the way the building code is written, if you do a prescriptive path, you're going to get a little bit more benefit as far as theoretical code compliance than if you're doing a performance. But in the performance path, the reason why we like the HRV is not so much to save the energy, simply because of the ventilation rates we have to use, but mainly for the health and well-being of the occupants. The HRV allows for some energy savings and code compliance because the reference building, the reference house, does not account for one. So if you put one in your proposed house, then that's a credit that you have over your reference house. But to get the full benefits of the HRV, the install should include a controller. And I know it might sound really odd, like, come on, really? People don't put controllers? Well, no, not everybody does. The controller should not be located in the furnace room, simply because the furnace room is probably the hottest and driest area of your house. Not very typical of what's going on in the house. You want to have that controller next to the furnace thermostat on the main living space of the house. And if you don't put a controller in, then really you're making your HRV a glorified fresh air intake. So might as well just go back to putting the duct in and call it a day if that's how we're going to install them. The other thing that we have to think about, and we've seen that here in Alberta, is if the HRV isn't interlocked with the furnace properly, the air coming out of the ductwork might be coming out cool. Now, I'm not saying it's cold, because human beings are hot. We're 37 degrees C. Now, if you think about it, there's not a lot of spaces or surfaces in a house that are at 37 degrees Celsius. What that means to us is that everything around us is colder than us. We will feel that everything is cooler. So if the furnace is interlocked with your HRV correctly or properly, the air coming out of the ducts when your HRV kicks in is going to be cold, quote unquote. So what we've seen here is people get bothered by that and they go downstairs and they unplug the darn thing. They unplug the HRV because the ductwork, the air coming out of the ducts is cold. And then the builder gets a call and says, I got cold air coming in through my ductwork. I don't want that thing working, blah, blah, blah. And so now we get into an airtight building that doesn't have proper ventilation, and then you get all the snowball effect of that. So again, when we design these things, we have to be mindful that we are dealing with living beings and not people that just take decisions on data like the conversation we're having now. So it's important to have a well-installed HRV. As the houses get more airtight due to the energy cord, the indoor air quality may be reduced and condensation risks may be increased. The HRV will assist in indoor pollutants, concentration of chemicals and humidity levels, and all that while you save energy. But having an HRV doesn't mean that you rule out completely the risks of condensation on your windows and mold in your house. There are other factors, but proper dryability in your houses is a key factor. So, air tightness quality control. How do we know if the Airberry was completed properly? how do we know what we paid for? And I think that's a great question, because you know, we have these conversations around what's the best way to build an air barrier, and different trades will just put it in their quote. But how do you know what you paid for? Like, how much money did you really spend figuring out all the detailing that comes with an airtight system? Like, can you really separate the materials from the labor on this question? And you might find that that differs from one building to another. I've had some builders tell me that to be at you know, 0.5 to 0.7 on every single house, they had to do 3 trainings every 3 months, and it took them 5 years to get there with their trades. And that means that they can't even have a turnover of trade. And so what were they paying for before they got to 0.7? So I feel that there's a cost question that needs to happen here to really see, you know, how much are you spending on your air tightness? How can we find out if your air tightness is done properly? And the lower air exchange rate will bring more benefits to the homeowner. So I'm reading my slide and I'm like, oh, I don't remember what I meant by that. But in a nutshell, how do we quality assure an air leakage target? Well, an air leakage test is the measuring tool. We can do that at pre-drywall. Again, there's some caveats. You don't want to tear out poly and all that stuff. You want to do it properly and cautiously. Some people will opt for a positive pressure test at pre-drywall with a big smoke machine inside, and then you see the smoke coming out. That could be a safer practice for groups that might be more comfortable with that approach, because now you're not ripping out poly down the walls and ceilings. And we can do a occupancy test. So what we like to do is both, because that's the delta that we have to work with in simulation modeling. PHBI offers a series of theoretical and on-site testing training to help industry understand all this. And yeah, so PHBI has a lot of courses that might be a good tool for any of you to tap into to really understand, you know, how we can troubleshoot this and make sure that we're doing a good job. So what is a good performing air tightness target? Right now, when we talk to different groups across the country, 1.5 air changes per hour is okay. Okay. 1 is better. 1 air change per hour is what we would like to aim for. And that is mainly for the prairies, because we have a very harsh, rapidly changing climate. As soon as you get close to water bodies, like maybe Southern Ontario, BC, where the weather doesn't change as quickly, then you could be a little higher, right? It's not going to damage anything. But 1 is where we would like to be, 1 air change per hour. Again, caveat, 1 air change per hour on a standard 2,300 square foot house versus 1 air change per hour on a 8,000 square foot house. That's not the same 1 air change per hour. There's going to be a lot more air movement across the shell of the building on a larger building than a small one. So rule of thumb, the bigger the house, the lower the air leakage rate for the mitigation of risk is what you want to do. Okay, so after all this work, can we guarantee an air leakage rate to use it for code compliance and other energy efficiency target? Well, we can't really guarantee it, and anybody on the call or on the video that has done either EnerGuide or mandatory air leakage testing, you're kind of just going, okay, are we going to get there, right? So you do a whole lot of troubleshooting. You go on site pre-drywall, you troubleshoot, you talk to all your trades, you figure out all the detailing. Like, we can do it, but ultimately we all end up at occupancy and say, whew, you know, we got it. I don't like stress in my life, so I feel that there might be a better way. So as of recently, air tightness has been a challenge to execute without any guarantee of execution. In all simulation modeling, we had to assume the air leakage rate and hope that we get it right on site. But as of recently, there's a new product that came out, and it's called Airberry. And there is a dealer in your region if you want to get more information about it. But this actually just takes all the guessing game out of it. So it's worth exploring. It's really nifty. So what are the benefits of guaranteeing an air leakage rate? Well, The air tightness data can be used in your code compliance. And I'm going to give you a quick case study in a minute. If you can show a lower air leakage rate, then we can value engineer the rest of your project. Now, I'm not saying we're going to build cheaper. That's not the goal. But over the decades, and that's just a human condition, we get complacent, right? We do the same thing over and over again, and then we compound. And we start compounding stuff and adding stuff. And we never stop and question to see, okay, well, if I'm doing this now, do I still need this? So that's the exercise that I'm proposing we should be doing. If you want to get to net zero energy ready by 2030 and not break the bank, we kind of have to rethink a little bit what's needed, what isn't, considering the new technologies and the new practices that we have now that we didn't have, 50 years ago. Okay, trade-off air tightness for more relaxed performance values on your house and better HVAC sizing. Most, and I don't know if you knew this, many HVAC design software have a defaulted air leakage rate. And it's a ludicrous high air leakage rate. From what I understand, those values vary anywhere from 4 to 6 air changes per hour, and not every software can customize that value. So that's a big reason why most of our HVAC heating and cooling systems are oversized, because the air leakage rate that's used in the design is so high and it's not reality. So what you want to do is, if you can guarantee an air leakage rate, let's say we do 1 air change per hour, then you can talk to your HVAC team and say, hey, we are designing to 1 ACH. Make sure you model that, because my heating system will be cut down by about half. Now, you're not going to save a lot on changing that unit sizing, but what that will do is that unit, the downsized unit, is actually going to run properly. It will reach 96% efficiency, because if it's always on and off, on and off, on and off, like we usually see, those efficiencies are just theoretical. They never really get there. So to really use the technology, we want to make sure that those units are sized properly, just like driving a Hummer in a residential area, right? Huge engine, start, stop, start, stop. So yeah, you got a lot of potential energy under your hood, but you really don't get to use it, right? It allows for better performing house at marginal cost increase. Air tightness with or without air barrier is by far the most cost-effective way to get to higher performing buildings. And it makes net zero energy ready simple and cost-effective. So I'm going to give you a quick case study here. We did a quick cost analysis on include air tightness in the current, like an energy model, just for code compliance. Okay. So most houses, and we're just full disclosure, this is for single family detached houses. As soon as you throw party walls in, then that's another conversation. The results are the same, but the impact of air tightness is even better. So this is for a single family house, detached, an average size, production builder house. So most houses today comply to the National Building Code. I'd have to run the numbers to see it more accurately for the Manitoba Code, because the prescriptive values are different than the National Building Code, but I feel that they would be very close. Most houses at 2.5 air changes per hour are about 5% compliant. As you may already know, the code allows us 2 different air leakage rates to model, and that air leakage rate is determined by the amount of detailing that are on your drawings, on how your air tightness details are put together. Most houses in Alberta, we have attics, are 22 by 6 walls, 16-inch on center, 4-inch of 2-pound foam in your rim joist, 4-inch of 2-pound foam in your cantilevers, our 12 2x4 basements at 24-inch on center, no slab insulation below frost line, no radiant slab. Like, yes, we do have some, but let's go for a typical build. 96% furnace, HRV, a typical natural gas hot water tank, double pane, vinyl frame windows, and approximately 13% fenestration door to wall ratio. So we're not looking at mansions that are facing west, with full tall walls and walkout basement, just a typical build. The same specs that I just described, if we take the air leakage rate from 2.5 to 1.5 air change per hour. So we're pretty conservative here. We went from 5% compliant to 10 or 20% if it 20% compliant. So what does that mean to you as a builder? Well, as the energy codes get more stringent, if the air tightness is fairly low, the construction assemblies won't have to change as quickly. So basically, your air tightness allows you to buy time to adjust as the prescriptive values will start rising, or either the prescriptive values are going to start rising, or the performance path is going to get a percentage of betterness that will increase over time. You might not have to start looking at more difficult envelope system or assemblies for a little bit longer, because air tightness will keep the performance of your house to a certain level and with conventional practices. And a lower air leakage rate will offer you an opportunity to value engineer the current practices and keep the construction cost and materials down today. So again, it's not about building cheaper. It's about, building smarter, doing it better. So the moral of the story is, if Manitoba builders are already very good at air barrier systems and are mandated by codes to install HRVs, why not use this to your advantage in the performance modeling, which is also known as a full building trade-off. So people are going to say, but Em, when we do energy performance, the specs are going to change on every house. And as a production builder, I can't have that happen. I said, well, that's not really how it works. And so what we do is we would model and figure out a spec that would work for 80–85% of all your builds. And the odd time that spec doesn't quite cut it, then we would find a solution that's cost effective to make that one house slightly different. And we're not talking about, adding exterior insulation and heat pumps and all. We're just, usually there's small things that we can change just to tip you over that compliance threshold. So basically, instead of increasing your cost on every single house with a prescriptive path by compounding efforts, now you develop a spec that gets you there on most of them. And then on the one house that might not get there, that's where you spend a little bit of money. So when you do your cost, your budgeting on a yearly basis for all your building stock, then you're not adding cost to every build, you're adding cost of one house over all your builds. So on a business perspective, you kind of dilute that extra cost. So I always like comparing performance modeling to a sports team. Now I said team, it can't be a single person sport because there's only one person doing everything. But if you would take, I don't know what sport you're into, but whatever that is, if you would take all the best players of that one sport and put them in one team, you have to ask yourself if you are guaranteeing a winning team. Because now you're compounding all their salaries, but really, until they work together, you're not winning, but you're spending more. So you can optimize. I don't know if you saw, is it Moneyball with Brad Pitt? That's kind of what he did with his baseball team. He took every player and optimized which player would play in which position. They weren't always the highest paid player, but they were optimized in their plays, and he got a winning team out of it. So I think that, again, those are the kinds of things we have to think about when we start moving forward to the 2030 targets. So in summary, guaranteed air tightness makes meeting energy performance requirements easier, whether that's a building code, net zero, it doesn't matter. And yet you can guarantee it, by using technology, or you can guarantee it, or very close to, with a lot of site support. Either is fine. Either is fine. Ultimately, you just want to really hunker down and know that you will get to whatever target that you set. It mitigates moisture issues within the envelope system, from what I understand from our warranty partners here in Alberta. Attic rain, it's really funny. I don't know if you ever typed attic rain on Facebook or on social media, but there's a lot of talk about it. I don't know if you had a lot of that in Manitoba, but in Calgary for the last couple of years, it's been pretty bad because of our Chinook winds. So yeah, everybody's scared of it. Anyways, I get a bit of a chuckle out of it. Cost trade-off for air tightness for insulation and HVAC performance. So just like I mentioned, if you know the air leakage rate that you can achieve, now all of a sudden you can revisit the insulation you're using, you can revisit the sizing of your HVAC, you can revisit the distribution system of your HVAC. And so by doing all that, you can offer more benefits to the homeowner, more benefits to yourselves as a builder, so you reduce your liability, but for the same cost or very close to. So again, build smarter and not harder. So these are some of the courses that PHBI offers. So there's construction fundamentals, construction technology, energy efficiency and air tightness testing, problem solving in home buildings. And on the business side, that's really cool too, because I mean, like I said, we all want to build a good product, but we have to do it in a way that we're not going to go under, right? Nobody gets in business to go under. So we want to get more savvy on the business side, understand management fundamentals. Maybe there's some takeaways there. Maybe there's some new ways of managing projects that could save money on every job. Ethics in home building, fundamentals for home renovation. We all know that renovation market is a huge market because those units will also be part of the 2030 target. How we're going to get existing stock buildings to get to that target? Well, there's some solutions out there. I'll just keep it at that. And land development. So how does that work? They are a crucial part of this whole solution. Some of the decisions they make as far as architectural guidelines and controls are completely out of the builder's control. For example, if we know that every house on a whole development is going to be net zero ready, net zero energy, it's not right that the builder would possibly have to justify a cost difference of a few $1,000s for the same house built in the same neighborhood across the street from one another, because one might have passive solar gains and one might not. So how do we work around that? There's a lot of things that can be addressed at the architectural control level. The other one that we're struggling with is hip roofs. I mean, yes, they're pretty, I get it. But I can't do nothing with a hip roof when I have to put solar on. And yes, I can split it west and south kind of thing, but then because of the shape of the roof line, and I mean, the modules are not triangular, they're rectangular, so you lose a lot of space to optimize your solar array. So those are conversations that are happening currently with the land development teams. And then in sales and marketing, so how do we sell this stuff, right? So let's face it, energy efficiency is emotionally boring. And I use that quote from one of my longtime colleagues, it ain't sexy. Now, if you have a heat pump, a ground loop, a solar array, wind turbine, people are gonna have barbecues and talk about it and brag about it because they're gonna be so excited about it. But, you know, if you tell them that, you know, you have an R40 wall, they're gonna say, oh, well, you know, it kind of just sits there. Other than me putting pillows on the windowsill because it's cool, they're not gonna have parties for that. So it is really emotionally boring, and I find that we have to start selling our houses a little like we sell cars. So how do we touch the emotional chord of the general public by energy efficiency? Maybe we don't call it energy efficiency. Maybe we call it something else. And by the back door, they get an energy efficient product, which benefits you as a builder in reducing your risk of failure and all the things that can happen in transitioning to the 2030 goals. So those are some of the courses that PHBI offers. These courses can greatly help you achieve different programs for energy efficiency in your region. You probably all know about the Efficiency Manitoba program. It's been around for a few years already. So in a nutshell, with a prescriptive path, from what I understand from the charts that I got, you can get about $1,200 back from Efficiency Manitoba. Again, Lanny, if I'm putting my foot in my mouth, please step up later and set me straight. So that's free of charge to the builder. The homeowner. Efficiency Manitoba just sends you a check. As far as the performance offers, then that varies from $1,500 to $12,000. And just so you know, 20% better with a good air tightness is not a big deal. So 20%, you already get more than your prescriptive path. But you might have to spend a little bit more on the team that can do the simulation model, because not every fee will be covered by Efficiency Manitoba. They will cover all the leakage, the site stuff, but there's a set amount that's shared for them, for the team that does the modeling. So you might spend a couple $100 more. I don't know. That's between you and your contractors, your team. But I feel that there's a lot more accessibility in funding with the performance modeling. And so 20% is not a very difficult target. Now, that being said, if you have 5,000 square feet and you have, I don't know, 25 windows facing north on a walkout basement, yeah, it might be a little bit more challenging, but for the most part, 20% is not a very difficult target. CMHC mortgage insurance also apply. You can apply for single family or MURBs. That's built on the backbone of EnerGuide or code compliance. So depending on how you want to submit for your application, it's either a code analysis or an EnerGuide analysis. So if you have questions about that, I welcome you to reach out to CMHC. They have people in every region supporting markets to explain those different programs. But basically, if you use only the EnerGuide scale, you can get 15% on insurance premium refund to the homeowner. If you get to 40% better, then you get 25% back. I remember that when I bought my house 10 years ago in Edmonton, we complied with the 15% better, and I got about a $4,000 check. So, you know, it's, to the home builder, might not be a lot of money, but to the homeowner, you know, $4,000 in the mail is kind of nice. So, you know, we were quite happy about it. So these are the main programs that are available in Manitoba. I'm not aware of others. Again, Lanny, if there are others, please let the group know. But otherwise, thank you for listening in. If you have more questions, please feel free to reach out to PHBI. There's the email at the bottom there, askphbi@phbi.ca, and they will be more than helpful in helping you finding either courses that work for you or directing you to different people that they have worked with. I'll stop this share screen. Oh, I got one more slide. There we go. We have to thank our sponsors. So I had to go to the last slide. Thank you very much for listening.
Great. Thank you, Emily. That was fantastic. Just checking the chat to see if anybody has put in any questions, but if anybody has any questions, we do have time, so you can unmute your mic and ask away.
I have a question, Lanny. You hear me? It's Diego from KDR Homes.
Hey, Diego.
So I'm seeing around the city with houses that are almost 10 years old. You made a good point with the air barrier, and you said it's not vapor resistant, but maybe it should become vapor resistant, because we're seeing that houses using these the code to build the building envelopes, they're rotting from the outside, and there's actually no signs from the interior of the home that there's actually a problem in the wall cavity. So eventually we're seeing, I guess, the acrylic stucco or masonry falling off, etc. And as you obviously look into the matter and you start removing some of the exterior, you're finding that the sheathing is completely rotten. There's mold. You can have structural members that are rotten. Your sill plates are rotten. And you made a good point when you said, like, about people saying that my walls aren't breathing. So we do a lot of renovations too, and we have a house that's built in 1954, and we gutted the inside, and there is no vapor barrier and there's no air barrier. So the air barrier is the actual siding that's nailed onto this house. But I can tell you, from 1954, there's not 1 ounce of mold. There's not 1 ounce of rot. And the biggest problem I find with when you see these houses, and I just seen one yesterday on Loudon Road. It's a large house, maybe 5 years old. It's probably about 6,000 square feet. It's huge, and the whole exterior is removed, and it's all the sheathing on the walls decayed. Now, for a builder, we're following the code, making things airtight. And reality is, we're not designing. There's no design in the code actually to help, like I said, not stopping a vapor entering the wall cavity, and then it can't dry. So how do we get by that? Because I mean, it's going to come to the point of major lawsuits that are going to come about. And I can tell you right now, we have an area in Royal Woods, and if you actually go on the lakes, there's about 30% of the houses on the lakes have their exterior back walls completely redone. And I guarantee you that all of them have visited engineers. The builders are saying you're out of your warranty period. They visit engineers, someone's coming to fix it, and they're correcting it exactly the same way it was built. So because you have to follow the code based on the Airberry. So is it smart for you know to actually have an Airberry that's going to be vapor resistant then?
No, and here's why. That was a lot. There's a lot of questions in that one statement, so I'll do my best to answer most of them.
Sorry about that. Yeah.
No, that's fine. So, just to give a little bit of context, I will ask you a couple questions. That old house from the 1950s, how well insulated was it?
Well, it had sawdust insulation. It wasn't.
It wasn't.
Right.
That's the driver. So houses that were not insulated didn't have any of these issues because there was so much heat loss from the inside of the building that all those assemblies stayed warm year round. Okay, it's not energy efficient, but it works.
No, I'm quite aware of that. I'm quite aware of that. Yeah.
So air tightness in houses that are not insulated is not an issue. Air leakage, in a house that is not insulated is an issue. But as we start adding insulation, and that's what we're doing, that's where we have to start being more and more mindful, because now those cavities are becoming colder and colder and colder. So if you take the passive house standard, for example, I don't know if you're familiar with it, but basically a passive house wall in Calgary region would be anywhere from an R40 to an R60. Now, I'll let you figure out how to build that, but an R60, that's a lot of insulation. So the temperature differential and the gradient in that envelope or that component is huge. And that is why they have a mandatory air leakage rate in both positive and negative pressure of 0.6. because they have to be uber airtight. Now, air tightness is not a vapor retarder. It can be, it doesn't have to be. And in a lot of the passive house designs, they actually have vapor retarders, but not vapor barriers. So the walls dry very easily in both directions. The thing you brought up about the stucco, well, we've seen in Alberta too, there are multiple factors to why that's happening. The main one, well, I'll start by the first one. One, acrylic stucco is plastic. It has zero permeance, like water vapor does not travel through it at all. So now you're wrapping a full envelope system with something that doesn't dry at all. Right. Most stucco systems have either an EIFF system behind it, but then depending on the manufacturer that you work with, they may or may not have a rain screen. Not having that rain screen makes that EPS, and it's EPS foam, right? It's not extruded, it's EPS. The white styrofoam is directly to the OSB. That EPS drinks water. It will stay wet. And then so the water that gets in your wall doesn't necessarily come from the inside, maybe a little bit, but it infiltrates through tie-ins and then gets stuck between your OSB and your EPS. Correct. So having a rain screen with acrylic stucco is super important. If you were doing cementitious stucco, which I love cementitious stucco, people find it doesn't look very good because the grain's thicker and you can't really paint it, but it is more of a dummy proof finish, because one, it's fireproof, it's mineral based, so it dries water like no tomorrow. It can get wet, and you don't necessarily need that big rain screen. Now, warranty programs might say, oh no, I would like it even if it's cementitious, which is fine, but that's a part of the concern. And the other thing is your air leakage. Vapor diffusion is what a vapor retarder works at managing. And for the most part, vapor diffusion travels in a straight line. It doesn't go like that. Right? It kind of just leans on stuff and eventually hopes to get through the paint, the drywall, the poly, the bath, the OSB, the whatever is outside. Now, that takes time. And the reason why we have a vapor retarder is that we want to reduce that vapor diffusion until summer comes and then everything dries out. Right? So we're buying time. That's what the vapor retarder is for. So most times on envelope failure, vapor retarder is not the main concern. It usually is water vapor that gets stuck in the wall from the outside, or air leakage that carries water vapor with it in your envelope system. Now, as we add insulation, that cavity becomes colder and colder, so its tolerance for moisture gets really, really low. And that's why now we're talking about, is there a better vapor retarder than what we're already doing? And what I mean by better is I don't mean more watertight. I mean slightly less tight. And the reason for that is exactly what you described, is right now, that polyethylene that we use, if you start adding a whole bunch of insulation and you're creating that temperature differential, the water vapor pressure from the inside will be not much. It's not going to push that much. But if there is water vapor that gets stuck in your wall and doesn't have anywhere to condense and drip out, then it doesn't have anywhere to go, because that poly is so aggressive that it stays there. So we are debating, should we use a vapor retarder that is still a vapor retarder, but not as aggressive as the poly, so that whatever water vapor gets in there can actually escape to the inside. So there's a few, it's building science. So how do we start changing a little bit how we put things together? And if you look at a lot of the German passive walls technology, they have no plastic materials at all in all of them. It's all a wood-based, wood fiberboard, pressed wood insulation. It's all wood. And their vapor retarder is a 3/8 OSB, a 5/8 OSB on the inside. That's it. They don't have poly, and it works. That's what they call a vapor open assembly.
So I think, my point, I guess, is that, as products evolve and we're using it, and what's been happening here is, let's use a Hvac or Hvac air barrier, and then you're using a double scratch system with an acrylic finish. Reality is we're basically sealing the wall. The wall cannot dry, and it can be around from a window opening, or it can be any breach. It could be a shift, a crack, but so nothing's designed like in future. Like if a client didn't caulk their window or caulk a flashing detail, which is part of homeowner's maintenance, when they look at their wall assembly now, rotted, we're looking at a huge lawsuit, because obviously everybody's going to start pointing fingers on where best practices used, and even if you use best practices, you should have went beyond the best practices. So, and I think we went through an era here that acrylic stucco has been used quite a bit, and it's been used as a double scratch system to keep obviously competitive. Not many builders are using a full EIFS system. So what's happening is, like, we have a lot of stock here that's going to be problematic, and it's starting to show. I mean, this is what's happening. So I think, so as much as we make things, as my point is, as airtight as possible, there needs to be, I think, better building practices maybe placed in the code that we all have to obviously work with to stay competitive and ensure the life of the home, because these houses aren't going to last 100 years if this keeps up happening. Within 5 to 10 years, you're completely stripping the exterior, the wall assembly, and then you're redoing it exactly the same way you did it prior.
That's another piece of the problem.
The code. But you're following the code.
Just a reminder, maybe. The National Building Code is also the bare minimum. And the reason why I remind people of this is that we have 4 different main climate zones in our country. 4 time zones, 4 different climate zones. They're almost in line. And so to build a code that would work for all those climate zones, we have to know that some of that might not pan out in different climates. There's a big gap between Winnipeg and Vancouver.
So definitely, yeah, exactly.
Right? So we have to be mindful that best practices is not building code.
Understood, but I think that's
Okay.
maybe the code should be more regional. So
Well, that's why the provinces can have codes that supersede. So Quebec, Ontario, BC have the national code, but they have their provincial codes that are above the federal one, and that's left to the different provinces. Now, again, the provinces don't have to do that. Maybe that's something that the code will decide to implement, or maybe, as you suggested, they're going to start saying, okay, well, if you're in this climate zone, you need to do that. If you're in this kind, because that's what's happening now with the energy code. Now they separate it in different climate zones, right?
Right.
So there might be more guidance, but ultimately, the thing about codes and laws is that they're always made for the lowest denominator, right? So as an industry, or even as humans, we have to know that we can do better. But again, to your point, at what cost? We have to be mindful of the cost of changing things.
Right, thank you.
You're welcome.
I think we have.
Thank you. Allison just confirmed that I didn't put my foot in my mouth. I'm just looking at the chat box.
Yeah, no, she did confirm that everything there was accurate. Well, if there are any further questions, please feel free to you can email them to us or to PHBI, and we can get back to you. But Emily, thank you so much for your presentation today. It was tremendous. We really appreciate the expertise that you shared with us today. Thank you to our event sponsors again, the Accurate Technology Group and Federated Insurance, for sponsoring our virtual housing forum. And thank you all for attending this morning's session. Our next session is being held on Tuesday, November 17th at 2 p.m. With Ross Jardine from CSAM presenting to us on emergency preparedness for subtrades. Until then, stay safe, everyone. Have a great rest of the day. Have a great weekend, and we'll see you again next week. Thanks, everybody.
Thank you.
Take care.